In this video, we're going to begin our very first chapter in this course that's not part of the review, where we actually dive into a little bit of what designing experiments is all about. So again, this course is a basic introduction to design of experiments. Our goal in this course is to introduce a variety of different experimental designs and the analytical techniques that we're going to be using to address the data that come out of each of these types of designs. We'll also talk some about the benefits and why we might choose one design over another. By no means, though, is this course going to be a comprehensive look at design of experiments. I mean, we're going to look at a lot of them, but we're certainly not going to cover every one, and there's more that are being designed every day for different types of purposes. But hopefully after this course, you should have a good feel for some different approaches that you could take for different desired outcomes and different situations as they come up. Now, we may have mentioned this earlier, but the focus of this course is going to be on the design, not necessarily the statistical analysis. And for those of you used to taking traditional statistics courses, this might come as a bit of a shock or a bit of a change from what you've been traditionally doing. But it's important to call that out at the beginning. The statistical analyses that we're going to use in this course are not particularly complicated. And so I don't want you to spend an undue amount of time trying to focus on them or get an undue level of confidence if you master them, because that's not the point of the class. The point of the class is to understand the experimental designs and the consequences of using different types of experimental designs. And those statistics are involved in the sense that if I choose a different type of design, I will need to use a different statistical analysis. And then we're going to draw out and demonstrate the different kinds of statistical analyses that we could use. It really isn't the main focus of the class. There are other courses that cover the different types of statistics that we'll use and aren't about designing experiments. This is not that course. This is the course that specifically talks about design of experiments, and depending on what's offered in the future, this may be the only course that you take that doesn't really focus on the statistical analysis, but really focuses and takes the time to look at how we design experiments for statistics and data to be calculated and gathered. All right, so design of experiments, and this is the introductory chapter of the textbook, chapter 1. So we'll talk a little bit about why this course is necessary and why the goals of this course is important. We've already talked a little bit about it and how it differs from some of the other things that we do. We'll talk very quickly about the history of design of experiments. I think it's really interesting, actually. However, I do think that when we look at history, it's important to realize why we talk about it. And we'll talk a little bit about that too, but we're not going to spend too much time on it. And then some basic principles and terminology. This is a really big piece, and today, or this lecture set, I should say, not necessarily this video, but this lecture set is going to be the lecture set where we establish a lot of the terminology that we're going to be using throughout the rest of the course. And if we've done any review chapters, I've been intentionally avoiding that and using some of this terminology in those chapters until we've had this conversation. So from now on, I'm going to start changing the language to what is more statistically and methodologically appropriate by using some of the definitions that we're going to talk about later in this lecture set. The strategy of experimentation. And as I just mentioned, the strategy of experimentation is kind of the purpose of the course. Really looking at what are different ways we can construct experiments. Why would I construct an experiment in one way versus another? And maybe even what are the benefits and detriments of each of these types of experiments? Well, I shouldn't say maybe, definitely. What are the benefits and detriments of these different kinds of experiments? All of these go into the strategy of determining which type of experimentation I want to utilize. And one thing that students don't often realize is by having a comprehensive knowledge of designing experiments, one other piece that I can do is recommend, if a client asks me to design an experiment, I can say, well, you know, I can design it with the tools and methods that you're already using, and this is the outcome that we could look at. Here are the different types of outcomes and questions we can ask if you're willing to put a little bit of money into this, if you're willing to expand what you do beyond what you're already doing. So finally, we'll actually outline a series of guidelines for planning, conducting, and analyzing experiments. And this is going to lead up to your very first project in the class. And we do our first project very, very early. Don't worry. It's not going to be a particularly complicated project, so don't worry too much about that. But we do it very early to kind of get you in the hang of it. And we're going to jump right into the fire and have you doing a project. And we'll go through the guidelines for how you construct and utilize your own experiment. And hopefully that'll give a little bit of context to everything else we'll cover in the class. All right, so let's talk about this design of experiments. So what is an experiment? And that's a kind of an interesting question. An experiment's just a test or a series of tests, and usually there's a design behind it. Well, always there's a design behind it. We'll have a fun quote later. But it's not really more or less than this. It's a specific construction for a series of tests. Now, in statistics, when we talk about experimentation, we also have a series and labels that we apply to that, and we'll talk about that in a bit. Now, these experiments are used for a variety of reasons in a variety of different fields. We have them all over the place, and they're typically considered to be the gold standard of research. So what can we use them for? Well, we could use them for characterization and optimization. That is to say, what is the best way that we could do this particular process? We can use them for evaluation of different properties of materials. So what are these things good or bad at and under what conditions? We could use it for design and development of new treatments and drugs. So let's say we wanted to come up with a new treatment or vaccine. We use experimental designs to design thorough tests of these particular proposed treatments and some different comparisons that we can conduct and implement to determine the effectiveness of the treatment that we're proposing. Tolerance is an interesting thing that I wouldn't normally think about, and perhaps you wouldn't either. But how far can we bend a system before it breaks? Let's say I took a metal rod and wanted to see how far I could bend it. Well, we can have experiments that determine, well, how far can we push something before it breaks? What is the breaking point, and what's the variability of that breaking point? So experiments are really, really useful for determining system tolerance. Now, I mentioned earlier, all tests are designed, all experiments are designed. Some are poorly designed and some are well designed. But it is important to realize that if you're running a test or series of tests, there's some kind of design behind it. Even if people don't want to take the time to talk about experimental design, you're using some kind of design. You have some kind of plan, or even if you don't have a plan for the implementation got implemented in a certain way. And the method by which the experiment was conducted or the tests were conducted is the design. So all you have are bad designs and good designs. You don't have no design, because if you implement something, then you're following a particular method, or looking back after the fact or post hoc, you have followed a particular method, and thus you have followed a particular design. Was it a good design? Was it a bad design? Well, that's why we look at this stuff, is to try to implement good designs, but all of them have designs. I'll say that one difficulty and one reason that I always recommend that individuals speak to statisticians early on in the process is when we're asked to consult on a project that was poorly designed. I mean, imagine somebody who spent a whole bunch of time and money trying to do one or even all of these different things with a data set that they care about. And it turns out that they had a designed experiment. It was just poorly designed, and they implemented it poorly. There's unfortunately not a lot we can do. There's a fun quote that says to speak to a statistician after the experiment has been conducted is to ask for a post-mortem. He perhaps could say what the experiment died of. And that's a really good thing to reflect on. And when you're working with clients or eventually working with a boss, I highly recommend that you speak to them about this, because many clients and bosses don't know that they should take advantage of your skill set before the fact, and specifically the skill set you're going to gain in this class. so that as they're looking at evaluating certain properties, they're speaking to you about what methods could we use to evaluate this appropriately, and what methods would we use that would not evaluate this appropriately. And incidentally, you end up getting numbers at the end of the day. It's not that you can't run the statistics, it's the valid interpretation of statistics. And we'll talk about that a little bit later on. So why would you ever construct experiments? What's even the purpose? And so some of the things that you could hope is to reduce time. I want to implement an experiment so that the time to develop this new treatment is less. That is to say, if I collect my data more efficiently or in a more organized manner, I may be able to do more with less data. And if I can establish that a new treatment procedure works quicker due to a particular design decision and there's not anything else that has to be taken into account, wouldn't I want to implement a design that allowed me to get this drug on the market sooner, or to get this treatment procedure out sooner, or this product out sooner? Well, the answer is absolutely. So one big reason that we use experiments is to reduce time. Now, very closely related to this is to improve performance. We want to use experiments to get better performing out of treatments and processes and to evaluate that. Using experiments can also allow us to improve the reliability of measurement, performance, and the different products that we're studying. We can look at robust procedures, so that's kind of the opposite when we were talking about systematic failure or at the point at which it fails. What are all the points where it doesn't fail? So if I find that this metal bar can be bent with, a particular amount of force, then I can claim that that particular product is robust to being bent at anything less than that particular amount of force that it breaks at. And of course, evaluating all of these different components is the ultimate goal of an experimentation. Now, to think about the process, and this picture actually comes from your textbook and you can check it out. We have something that goes in and something that comes out that we're studying. So let's say we have that steel bar we were talking about earlier, and that goes in, and then there's some process that happens, and then something comes out. And we're looking to see, in this particular case, when does it break? So how much pressure does it take to break might be our output in that particular study. So the goal is to check this pipeline. Now, the interesting thing about this pipeline is that we know that there are other things that come into it. There's things that we can't really control. What was the weather on the day we did the experiment? What's the gravitational constant under which we did the experiment? These are things that aren't really reasonable to control. But there are other things that we could control. We can control the nature of the machine that's being implemented. We can control the leverage that's being used on the particular steel. We can control the thickness of the steel. Perhaps we could even control the material. If we are working for a metal processing plant, perhaps we could create different materials that we're making the steel bar out of to help determine how much pressure it takes to break that particular thing. So our goal in an experiment is to look at these controllable factors, account for the uncontrollable factors, to better understand the process by which the input becomes the output. So the four eras in the history of design of experiments, this started in the early 1900s. Depending on where you want to look, Ronald Fisher is called the father of modern statistics, and he's a good place to start when we look at designing experiments. He's the person who came up with the main analysis that we'll end up using, the ANOVA. And through his research, it was primarily agricultural. Individuals were looking at how can we grow more crops more quickly. So what they were looking at is crop yield. Well, they were looking at a variety of things. One of them was crop yield, maybe the easiest to think about. And then looking at what are some different factors that can improve crop yield. So the input was maybe the general amount of work, or maybe even nothing in this particular case, and everything was a controllable factor, where they were taking the crops planted and seeing, can we change some of these controllable factors so that the output, the yield of the crop, was improved. And again, they studied many things, but they invented many of the designs of experiments that we'll talk about in this course and future videos. under this agricultural lens, and that's a main derivation for where a lot of this comes from. And if you look at the old examples, you'll see a lot of agricultural examples, and that's why. So in the 50s, we started getting into the first industrial area. Box, we'll talk about him just a little bit later on. And started talking about this concept of response surfaces. Now, depending on how much time we have during this semester, we may touch on response surfaces. If you're interested, please read ahead in your textbook. Response surfaces is one of the later chapters, but is a really interesting topic and a really fun topic, especially if you have a background in regression. Response surfaces should make a whole ton of sense and not be particularly complicated. But they started being introduced in this industrial era, and we started looking at this broadening out the agricultural impacts and the agricultural origins of design of experiments, and looking at impacts in other fields. So what about the industry, the greater industry fields? And again, it makes sense that this comes up with the industrial era, as we're looking for more efficient industrial techniques. So in the second industrial era, we're looking at quality improvement. So this is going through the early 90s. We're looking at how can we improve our quality of our companies? How can we improve the quality of our trainings? There's a kind of the lid of Pandora's box got blown off in these two, where again, we started in agriculture, but then we started opening, and it just kept opening. You can think of it like an upside down funnel, where it started in a very narrow field and then really broadened out over the 50s to 90s in where it was being applied, this idea of design of experiments. Also tied in things like robust parameter estimation and process robustness. So this idea of robustness certainly comes into play, but it wasn't until rather recently in the grand scheme of things that we did started talking about these concepts of robustness and where they're appropriate. And then finally, that brings us to, we'll call it the modern era, though it does feel like it's moving on very quickly, but we'll call it the modern era, starting in the mid-90s and moving to today, where we're continuing to apply experimental design in a variety of different areas. And it doesn't always work out in the ways in which we'd think it would. It doesn't always work as efficiently as we'd like, or lead us to the types of conclusions that we want to see. But it is something that people are trying to implement. You can think of industry, you can think of education, you can think of virtually any field that you want. And now we're seeing things like ANOVA and the experimental design starting to appear in all these fields where appropriate. Again, I mentioned earlier, design of experiments and experimental design processes have become really the gold standard in research, and that's not in agricultural research, that's not in industry research, that is in research in many companies in many different fields and areas. All right, so let's dive into the history lesson real quick here. We just talked about the history of the field, but let's talk about some of my favorite individuals. We have William Gossett. So Gossett was an employee of Guinness, of all things, and so he worked for the beer manufacturer Guinness, and really was studying how he could look at some of the different variables he was studying with small sample sizes. That was his big thing, is that he was really looking at small sample sizes and trying to figure out how could he do this analysis with small sample sizes. He ended up becoming the creator of Student's T distribution and worked very closely with Fisher to create that. And he wasn't allowed to publish his research. So William Gossett, because it was I should say the story is that because it was viewed as too much of a competitive advantage that Guinness didn't want to give out, then they wouldn't let William Gossett publish. So he ended up publishing his results in secret. And so he sent in letters to the statistics magazines, or the statistics journals at the time, and published assigned them as a student of statistics and introduced his t-distribution. And actually that story is where the name student's t-distribution is, and you can see William Gossett was the student in student's t-distribution. So of course Fisher himself is called the father of modern statistics. He's also been called, let me see, I pulled a couple quotes here, a genius who single-handedly created the foundations for modern statistical science and the single most important figure in the 20th century in statistics. He created a whole ton of different designs, was involved with these experiments, and did the ANOVA, designed a process called maximum likelihood and some of the properties of its estimators that are extraordinarily important in modern statistics today, and a variety of other things. So R.A. Fisher is a very, very well-known figure, and many of his phrases are often quoted. Another very quotable figure is Box. Now, Box, actually both of these guys are British statisticians, and Box has been called one of the greatest statistical minds of the 20th century. One transformation that we use when our normality is not justified is a transformation called the Box-Cox transformation, which he is known for making. And then one of his favorite quotes that I absolutely love is, "All models are wrong and some are useful." It's one of my favorite sayings, and it is extraordinarily illustrative of actually what we're doing when we're doing statistical design. So in this video, we've done a bit of an introduction and a little bit of a history lesson. In the next video, we'll go on and jump in with some of the basic terms that you'll need to know through the rest of the class.